Here's a picture of me and my Bearcat card. All right, question 1. Suppose we have the sentence P of x with the domain S. An existential quantifier would be there's an x in S such that P of x. So this is of the form there exists x in S such that P of x. A universal quantifier would be for all x in S, P of x, and that would look like for all x in S, P of x. An example, let x and y be integers and P of x and y be x plus y equals 4. So if we have for every x in z, there exists y in z such that P x of y, or x and y, this would be true because for every x, you can find a y such that x plus y equals 4. But then if you have there exists y in z such that for every x in z, P x and y, this would be false. Because you cannot find a y such that for every x, x plus y equals 4. Question 2, the principle of mathematical induction. For each n in the positive integers, let P of n be a statement. If P of 1 is true, and we have P of k, if P of k, or P of k implies P of k plus 1, if that is true for every k in the positive integers, then P of n is true for every n in the positive integers. So here's an example that you could prove by standard PMI. For every n in the natural numbers, n squared is greater or equal to n. So n has a least element of 1, so therefore it is well ordered and you can use standard PMI. An example that you cannot prove would be for every n in the real numbers, n squared is greater or equal to n. So the real numbers have no least element, so it's not well ordered and you can't use induction. All right, question 3. So we have an equivalence relation where you suppose a relation R on the set S. It would have 3 properties. Number 1 being reflexive for every x in the set. X is relation to x. Number 2, symmetric for every x and y in S. X is relation to y implies y is relation to x. And then 3, it's also transitive for every x, y, and z in S. If we have x is relation to y and y is relation to z, this implies that x is relation to z. Okay, and then for a function, the definition is let a and b be non-empty sets. F is a function from a to b denoted f a to b if f is a relation from a to b such that every element of a is related to exactly one element of b. Okay, examples. So an example of an equivalence relation would be let R be a relation on Z given by ARB if A and B have the same parity. So this is an example because it has the 3 properties where it's reflexive, symmetric, and transitive. An example of a bijective function would be the function z to z given by f of x is equal to x. So this is bijective because it's both onto and it's also 1-to-1. An example of something that's not a function or equivalence relation would be a relation on Z such that R is the set containing 1, 1 and 1, 2. So if you look here, we have 1 is related to both 1 and 2. So that means it's not a function. And then also, it does not have the 3 properties where it's not reflexive, symmetric, and transitive, so it wouldn't be a equivalence relation either. Thank you.